Hello everyone and welcome back to another video. As you can see, I'm now in this software and I'm going to use this software to show you some really cool thin section scans from some of my rock samples. Now, over the summer I collected some mafic samples like basalts, and these are extrusive volcanic rocks from a volcanic field in Montana. So I collected these samples for not only geochemistry and isotopes, but also some thin section analysis to do some petrology, essentially. So these rock samples, I had to cut them into billets, and I sent them out to be turned into thin sections, and it took about a month or two, but they finally arrived. And after they arrived, I used a microscope to look at them, but then I had them scanned in a PET scanner that we have on our college campus. And that process took quite a while because I have about 24 samples, and to fully scan each sample of thin section, it took about 6 to 7 hours. So it took an entire week to scan all my files. And I'm going to show you some of them here today using the software. So I'm going to go ahead and open my first sample. Now here it is. This is the full view of the entire thin section. If I was to use a microscope, you would only be able to see a small portion at a time, such as maybe that on the lowest magnification setting. A microscope is super useful for mineral identification and doing petrology. So I am limited using the software, but I can still do some useful things. For instance, I can turn on this scale bar. Hopefully you can see that. And it changes as I zoom in and out. I can also create scale bars and a couple other things. I'm still getting used to the software. So one of the first things you notice, it's kind of dark. There's some black and white. There's some colors here. And one key thing to know about microscopes is there's two main views that we use. There's plain polarized light, PPL, and then there's crossed polarized light, XPL. This view that I'm in right now is XPL, so the crossed polarized light. And that's essentially blocking off, I believe it's about half of the light. And when you do that, the remainder of the light, the remaining light, when it interacts with the crystal lattice of a mineral, it will interact uniquely depending on the mineral, and you'll get these interference colors known as birefringence. But you can use birefringence to help you with mineral identification because each mineral will have its unique birefringence. Now, for example, quartz is super low, so it's going to be white to black, same with feldspars, while other minerals like olivines will have high order colors, such as second or third order. And based off of the thickness of the thin section, which mine is 30 microns, and the colors it gives, you can use that, this chart to identify a mineral. So I just hit split, so you can see this upper left corner, that's plain polarized light. So that's just all the light coming through, and you can see pretty much everything's clear. You can still do some mineral identification with it. There's some key things that you can see in plain polarized light, but a lot of it is done in cross-polarized light. And maybe in a future video, I can go more in depth, and it'd be really cool, but really expensive if I could get a hold of my own microscope with a camera and show you that way. But that'll probably be a far future event. But that would be really cool. But for the most part, I'm going to stick to XPL when I'm talking about minerals. Now, when in XPL, with a microscope, I can rotate the stage. And as I rotate the stage, a couple things are going to happen. And I can simulate that in the software using this fading down here. So I'm at 0 degrees. Watch what happens when I increase to 75. As you just saw, the colors kind of changed on a couple minerals. They might have been initially really bright, and then they went dark, and then they came back. You'll see maybe there's some weird patterns in a couple of them. So when you're rotating a mineral, basically you're going to get a really bright interference color, and it's going to go dark. And when it goes dark, that's known as extinction. And extinction can be unique depending on the mineral, and sometimes mineral extinction can be helpful for identifying a mineral. There's different classes of mineral, and there is one type that will stay fully extinct no matter what. It might be clear in PPL, but if I was to look at it in this view, it would always be extinct. And those are isometric minerals. Those will remain extinct completely in a 360 rotation, and a mineral that does this is garnet, for instance, but there shouldn't be any garnet in any of these lavas that I'm showing you here today. Just a quick example of what's happening here. But let's get into the fun stuff now for mineral identification, right? So I said that these are mafic rocks. These are mostly basalts. And since they're mafic rocks, well, they're going to have mafic minerals. And one of the more common minerals that you find in basalts is olivine. There's quite a lot of olivine in here. And olivine has high second to third order interference colors, so birefringence, which you can see right here. Here's an olivine crystal. And here's another olivine. And yet another olivine. Now, you'll notice these weird things here. They're kind of dark. They're kind of gross looking. These are also olivines. Why do they look different? Well, the key thing about olivine is stable in the mantle. When it is brought up to the Earth's crust, it becomes unstable. And when it becomes unstable, it starts to deteriorate into a clay mineral, or multiple clay minerals, and the catch-all term for this is iddensite. So these olivines are being instantized, or turning into iddensite. So you'll see these fractures in the olivine. They're kind of turning brown. This olivine's really bad with it, so this is being fully altered and breaking down into iddensite. So a lot of the olivines are being instantized, I believe is the term for it. And you can see this is a nice olivine crystal here. Very euhedral. If you're not familiar with what that term means, think of a beautiful quartz crystal, or any crystal, if it has crystal faces. When you see crystal faces, it's euhedral, when you can see the actual shape of the crystal. If it's just kind of a blob, think of like a quartz vein chunk, that would be anhedral. If it's somewhere in between, it'd be like a subhedral. But for this crystal, this is a nice euhedral olivine. You can see the crystal shape of it. And then maybe, like something like this would be more anhedral. There's not really any defined thing happening here with it. It's just kind of a chunk of crystal. Something else to know, if you're not familiar with minerals, there's this thing called cleavage. Some minerals have it, some minerals don't. If a mineral doesn't have cleavage, it will have fracture. So what this is basically how the mineral cleaves apart. Some minerals have 1 cleavage, some have 2, 3, 4, and so on. Olivine has no cleavage, which means it has fracture. So if you were to smash this with a hammer, it would just break in random fracture patterns. There's no consistency with it, right? Now, minerals that have cleavage, they will be consistent in their breaking pattern. So if I was to break it with a hammer, it's going to cleave in a repeating parallel phase. It's going to be repeating breaking lines. And one mineral that's really common that has cleavage in basalts is pyroxene. And right here are a couple of pyroxenes. So this big crystal right here, this is a pyroxene crystal. You'll see this big line going right through it. That is not a cleavage plane, but that is twinning. So sometimes you can see twinning of minerals. So that's a twin plane right there. So if I was to rotate the stage, you'll see. This actually is not a good example of it. Maybe on this one, actually. This also has twinning. So the cleavage in this pyroxene is not really easy to see, and sometimes you won't always see cleavage. Even if a mineral has cleavage, you won't always see it. It depends on the orientation too, because the minerals in a volcanic rock like this, they're orientated all over the place when this thin section is cut in one plane, right? So you're going to see minerals in all kinds of different orientations. So it has to be lined up just right to see everything perfectly. Yeah, like right here. Here is a pyroxene, right? You can kind of see this. The cleavage isn't presented very well, but you can see there's some repeating lines. If you can see my mouse, we have a repeating line here. There's another one here. And they're all going in the same direction. They're parallel to one another. That is cleavage in this pyroxene. And pyroxene typically have 2 lines of cleavage. So this one's oriented in such a way I'm only seeing one plane of it. But if it was oriented another, I might see 2 planes of cleavage at the same time if I was looking down, for instance, the z-axis of the mineral. And the cleavage planes for pyroxene typically cross each other at 90-degree angles. You might have heard me say the axis of the crystal. So crystals have different axes. So looking at this crystal, this is a nice pyroxene, right? You can see here's the point of the crystal. Here's another point of the crystal. We're looking at the side view of the crystal, which means we are looking down, I believe, what is called the A-axis. We're essentially looking down the side axis of the mineral. We're not looking down the long axis. So if we were looking straight down from point to point, basically the top of the mineral, this would be the C-axis. This would be what is known as the optic axis of the mineral. And since we're looking down the C, or the A-axis, the side axis, we're only going to probably see one zone of cleavage. Kind of hard to tell if even this one. But remember that, because I'm going to come back to that when I show you the next thin section. I wish I would have discovered this sooner. It just made the view so much bigger. So this will be even better to show you guys stuff now. Where was I? Oh, we were talking about pyroxenes. So pyroxenes, there's two different types of pyroxenes. There's orthopyroxenes and then there's clinopyroxenes. And one way you tell the difference is you look at the cleavage, and there's a very specific thing you do with the cleavage. So in a microscope view, you have crosshairs. You have one line going straight up and down. You have another line going from side to side, like a crosshair. And let's say you found yourself a pyroxene that shows cleavage. We'll just use this as an example. And you look at the cleavage lines, and what you would do is you would rotate the stage. And you see how it goes extinct and it comes back out of extinction? So if the mineral goes fully extinct and the cleavage line is parallel to your crosshair, so either the side, your horizontal crosshair or your vertical, if it lines up to that crosshair and it goes fully extinct, that would be an orthopyroxene. So orthopyroxenes have parallel extinction. So orthopyroxenes have parallel extinction. Now clinopyroxenes have the opposite. So if your clinopyroxene goes fully dark, but the cleavage lines are inclined, so that maybe it might be at a roughly 45-degree angle between your two crosshairs, so they're not lined up with your crosshair lines at all, they are inclined to them, that would be a clinopyroxene. So clinopyroxenes have inclined extinction. And I don't know how possible it is to do that with this software. That is something that is more specific and easier to do with the thin section on an actual microscope. So hopefully that was clear, but again, I could maybe do this in a future video with a real microscope. That would be pretty cool. But here's another pyroxene with twinning. Enough with the pyroxenes. You've probably noticed these other weird minerals, like these big ones with the stripes. Here's another one here. These are plagioclase feldspars. So plagioclase is kind of I wouldn't want to say a catch-all term, but it's a generic term for the feldspar because I guess you could say it's a family, because there's different types of plagioclase. So plagioclase is just a basic classification for the feldspar. It doesn't really tell you what kind of plagioclase it is. Basically, what controls the composition of plagioclase is one is more sodium-rich, and one is more calcic, so calcium-rich. And depending on that percentage, will put you into a specific field on a certain chart for identification. So if I was to use this specific chart, one thing you do, and again, it would be easier on a microscope, is it all comes down to the angle. So you see the striping here. So those are not cleavage lines. Now, feldspar does have cleavage, but those stripings are twinning. And this specific twinning is really common in plagioclase. That's actually what you use to identify it as plagioclase. It's known as polysynthetic twinning. So what you can do, if you use this specific graph, let's say I'm rotating my microscope. Again, this would be easier on a microscope. And you can see right about here, both sides, if you see that center line, twinning line, both sides are about equally white now. So that's where my starting place would be. So that looks like, we'll just say about 14 degrees. Then I'll rotate the stage in one direction until I get to the darkest point, which you see, I just went past it. So I'm going to go back to the darkest point, and it's right about there. That's the darkest point. So I'll take, let's say that's about 46 degrees. So I'll do 46 minus 14, and whatever that number is, I'd write that number down, and I'd go back to my original starting point, which was what, about 14 degrees? I'll then rotate it in the opposite direction until I got to the darkest point, which would be right about here. I would then subtract that number, so I'd have two numbers in total. I would add them together, and then divide them by 2, and whatever my final number is would show me where I would be plotted in this chart, which would give me the identification for this plagioclase. Now, you wouldn't want to just do it to one mineral and call it a day. You'd want to do it to a statistical number in the thin section so it accurately represents all the plagioclase in here. And then that'll tell you what kind of plag that you have, and it might tell you something about the formation of the rock. So a couple more things. You'll notice there's a lot of crystal sizes here. You'll see we have the matrix, the background minerals, which are a lot of plagioclase, pyroxenes, even some olivines. And then there's some much larger crystals. The larger crystals are known as phenocrysts. And then, of course, all the backgrounds, that's part of the matrix. So the matrix stuff, the background minerals that are really small, those are all minerals that crystallized out from the lava. So lava is going to cool quickly, which is not going to allow the crystals to get big. However, in a magma chamber, since you're deep underground, you're insulated, things are going to cool a lot more slowly, which is going to allow for larger crystal growth. So these larger crystals, like this olivine here, this olivine did not grow out of the lava. This olivine was growing in the magma chamber. And then when the magma erupted through the volcano, this was pulled up into that conduit and erupted into the lava, where it then became part of it. You can see there's also phenocrysts of plagioclase, we got phenocrysts of olivine, and there's of course phenocrysts of pyroxene. And when we have a bunch of phenocrysts spread out all over through the lava like this, we would refer to this as a porphyritic texture. Now you might have seen this massive thing here. This isn't one big crystal. This is multiple plagioclase fused together. And typically you'd have other minerals as well, besides just feldspar. But this, when it's a whole bunch of phenocrysts all glued together like this is called a glomerocryst. There's actually another example somewhere in here, and it's not just one mineral. One large mineral. Here we go. So we have some olivines fused with some pyroxenes and a plagioclase. So this is a glomerocryst, so this is another chunk of the magma, and this is probably like, well, obviously a larger chunk of it, so this could have been the magma mush that got pulled into the either existing magma when it erupted, or maybe some new magma came ripping on through, and this got incorporated into the conduit, and it erupted at the surface at the volcano. So, I don't think I told you where this rock is from, right? So, this rock I took from the summit of an extinct volcano, a volcanic plug known as Black Butte in the Gravelly Range in Montana. So this volcano erupted about 28 to 30 million years ago, and it's an eroded plug. And this thing came erupting on through a lake. We think it came through a lake because it's completely surrounded by mudstone. When you look at this thing, it just looks like an eroded volcanic plug, an intrusive plug, and that's mostly what it is. You can see some really nice columns of basalt. But when you go to the summit, you can actually find pieces of volcanic material from a cinder cone. There's all kinds of volcanic scoria and volcanic bombs all over the slope up there. So part of the cone from this volcano still exists, which is impressive because it's super old. And this specific sample came from the conduit area near the summit, which was feeding the eruption. So this is the stuff that was coming up through the neck of the volcano and erupting at the surface. And with that, I'm going to move on to the next sample. Here's the next sample. This is also from Black Butte, the summit area, but you can see it looks completely different. So, as I said, lavas typically cool quickly, right? But this is a part of the conduit that was likely shielded and insulated, and was probably degassing, as well as releasing fluids. And this allowed the magma to start evolving compositionally, and also allowed for larger crystal growth. So you can see there are some massive plagioclase crystals here that take up most of the view. So let's go zooming on in to this thin section here. So all these giant white stripy minerals, these are huge plagioclase crystals. You can see there's also some olivines in here. Those are purpley blue looking minerals, those are olivines. But you'll also notice that there's this weird orange stuff, right? Right here. So this is calcite. This did not form in the magma, this is after the fact. So again, these rocks are super old, and they've been weathered and altered, and some kind of fluid came in that had calcite, and it deposited all kinds of calcite mineralization. So this rock has been altered, which is not good when it comes to my research geochemically, because, well, when a rock's been altered by fluids, it can not only remove minerals and elements from the rock, but it can add to it, like this calcium here. So, a bit unfortunate, but really cool to see in thin section. Some of the hand samples, you can see really cool cavities full of calcite crystals, like essentially like a geode, like a calcite geode. Here we have a nice pyroxene. You can see the cleavage that I was telling you about. See those parallel lines going side to side? So that's a pyroxene. And there's something else in here that I initially misidentified as a garnet. Like right here. Looks like a garnet. It's completely extinct. And as I rotate the stage, it stays extinct. So it looks like a garnet. But it's not a garnet. This is actually an apatite. And the reason why it's staying fully extinct is we're looking down the long axis, the C-axis. And because it's apatite, you can see the sides are all pretty much the same, and it's acting like an isotropic mineral. In the key of isotropic minerals, like garnet, their dimensions are all the same, no matter how you look at the lattice of the crystal. It's all the same in all the directions. The A, B, and C axis all equal, and all the angles between are equal. And because of that, the way the light interacts with this mineral, it's going to give off extinction completely all the time. Now, there are some apatites somewhere that are on their side. I believe this is one right here, actually. Yep, this is an apatite on its side. And when you view it the side view, you can see it goes in and out of extinction. These little needles right here, those are also apatites. So when you view apatite on its side, it won't work because you're not looking down the optic axis. So it'll go in and out of extinction. But when you are looking down the optic axis, which is the long axis, basically from the long end of the crystal to the bottom, looking down, essentially from a top view, it'll be extinct like this. And in a microscope, you can use this to do some really cool things, optical properties with it, to do some mineral identification, which might be something I can get into in a future video. But it's basically, this is how you would tell if a mineral is uniaxial or biaxial. And maybe, if you're curious what that even means, I'll leave that up to you to do some online research. And I'm sorry if I'm throwing all kinds of scientific jargon into this video. I know all these terms that you probably have no idea what's happening, but I hope you're at least appreciating the pretty imagery here in these thin sections and all the cool minerals. So again, I am not an expert myself. I'm still learning. So when it comes to mineralogy and petrology, I still have a lot to learn myself, but hopefully I can share some cool things with you and maybe you'll learn something, even if I don't fully explain myself. But yeah, we have apatites all over the place in here. I know there's more. They're kind of hard to see, but once you see them, they stick out. Something I didn't talk about is a mineral's relief. And this is typically something you want to look at in PPL, but I'm not going to switch back because I've already tried this a couple times, and for whatever reason, if I mess with the settings too much in this software, my screen stops recording, and I've already had to restart this process twice, so I don't want to mess with it. Relief is essentially how the mineral sticks out. So you look at the grain boundary of the mineral. So this is how much the mineral sticks out on the thin section. So quartz, for example, has super low relief. So if you just had one single quartz grain on your glass slide and you were looking at it in PPL, it's just going to blend right in almost. You might not even see it. And if you had a grain like maybe a clinoproxene with a higher relief, the grain boundary is going to stick out a little bit more because it has a higher relief than the glass. And it's also possible for something to have a lower relief to the glass. But that would be like a negative or positive relief, depending. And that's something you can test for in a microscope. It's a lot easier. You can't do it in this. Here's some apatites, actually. So you can see they're sticking out pretty well. They have pretty defined crystal boundaries. So I would say this is a moderate to high relief compared to something like quartz or FELDSPAR, which is lower. But everything stands out right now because it's an XPL. If I went to PPL, a lot of things might look really faded, and it would be really difficult to identify what everything is all at once. And this actually is a really nice example of a peroxene where you can see both cleavages. So you can see parallel lines going in this orientation, and then you can see them going in this orientation. And they intersect each other roughly at a 90-degree angle. It's not perfect. It's actually not 90 degrees if you look it up. It's more like 87 to something, rather. 94 or something. It's not perfect, but that's a nice euhedral peroxene right there. Inside a plagioclase with apatite nearby, with olivine. And there's actually one other mineral I want to show you here. And it's right up here. It's this mineral here. Now, this might look like a peroxene initially, but it's not. It was kind of hard to spot, but somewhere in here, you can actually see two different cleavages, and they intersect each other roughly at 120 to 60 degree angles. And that's something really that occurs in a mineral called amphibole. So this is some type of amphibole mineral. And amphibole, there's several different types of amphiboles in composition. One example would be hornblende, but I'd have to do tests to determine if this is actually a hornblende or a different type of amphibole. And I'm going to lean towards a different type of amphibole because typically in thin section like this, amphibole would be green, and this shows no, hornblende would be green. This amphibole shows no sign of green at all, so I don't think it's a hornblende. So it's likely some other type of amphibole. And it's typically something you don't see in the basalt. You don't see it in any of my basalt samples at all, except this more evolved rock, which is also from Black Butte. And let's look at this nice euhedral pyroxene right here. At least that looks like a pyroxene. The interference colors, it kind of looks like an olivine, doesn't it? But you can see there's some really repeating lines here, so that makes me think that's all cleavage. But maybe it is an olivine, and it's just giving the illusion. But anyways, so let's open up another sample here. So here is a very different looking sample, and this is again from Black Butte, but this is a bomb. This is a volcanic bomb, and this is a chunk of the magma that was thrown and ejected out of the volcano, went flying in the air, and came plopping down on the side of the vent. And because of that, it's super gas rich, and it cooled relatively quickly, unlike the last sample I just showed you. So if you have any kind of lawn lava rocks in your flower beds that are red and have tons of holes in them, that's essentially what this is. But this was on a larger scale. The sample I took was a little smaller than a football, but definitely bigger than a softball, somewhere in between. And this type of rock is going to be really gas rich. And you can see there's these big dark holes. And something I forgot to mention, glass and volcanic glass, so the glass of the thin section and volcanic glass will be completely extinct, black and XPL. So the fact that this is black here, these are actually openings in the rock. So we're seeing right through to the glass thin section. So this is what they call a vesicular texture. These are gas pockets that essentially formed in this bomb as this thing was cooling. The gas was trying to escape from this molten mush, and it was likely expanding. And it looks like it was expanding right along this line here, because there's a lot of these vesicular bubbles forming in this little line right here. So this is likely near the crust area of the volcanic bomb. And then, of course, down here, there was a lot as well. And there's some other smaller ones that kind of are spread out throughout the bomb. Something else you might notice is the plagioclase waves. So plagioclase is really good at showing flow direction. So if we had a lava and it was flowing, plagioclase can align themselves in the direction of the flow. This is a lava, but it's not a lava flow, or it didn't come from a lava flow. This is a volcanic bomb. So what might have happened is after it landed, it's cooling, it's still molten. It was probably maybe compressing itself a little bit, kind of flowing out, degassing. So maybe you had a little bit of flow action happening here, and just enough for it to all align the plagioclase all in the same direction, as you can see here. There's also giant phenocryst. We have a really nice pyroxene right here. Again, you can see all the cleavage in it. Really nice euhedral pyroxene. We also have some glomerocryst in here. Here's a glomerocryst, so again, likely a chunk of the magma chamber that got pulled into this eruption and incorporated in the bomb. There's a lot more. There's another glomerocryst. You can see it's a couple minerals together. There's another really nice phenocryst of pyroxene here. There's some of plagioclase, another really nice pyroxene. Some really big ones as well. And you can see kind of how the flow texture in this bomb kind of wrapped itself around this grain, maybe as it was kind of rotating in the mush as this bomb was cooling down. Or maybe this all occurred while it was flying through the air, because as it's flying through the air, it's cooling, but it's also molten, so the air rushing around the bomb can actually shape it, and a lot of them will take on a bomb or missile-like shape to it. It's interesting. Some of them look like little mini footballs almost. So let's move on to another sample. All right, so this is going to be the last sample I showed you. So the last three were from Black Butte, but this is from a lava really far away from Black Butte and significantly younger, apparently. Current age dating puts it about 16 million years old, and I can't remember the name of the valley, but it's really close to the Anaconda Range, I believe it is, the mountain range there. There's geologically something known as the Anaconda Metamorphic Core Complex, and it's roughly right up in there. Now, this is a mafic rock. The last ones I showed you are probably basalts. Now, this rock is not a basalt. This has a lot more alkaline metals, or alkaline elements, I should say, and it also has lower silica. This is a basanite. And you can see here we have a huge glomerocryst. So this is a big chunk of likely the magma system, probably from the intermediate magma chamber or maybe a really shallow crustal magma chamber that got pulled up in this eruption and incorporated in this lava. And we have a huge pyroxene here. There's something really interesting about this pyroxene. If we come to the edge of it, you can see this pinkish halo that goes all the way around it. Now, a really common pyroxene is augite. And if you have a pink rim on your pyroxene, this makes it likely titanium augite, which is or can be found in basanites. So this is a titanium augite. You can see there's another one right here. You can see that pink halo a little bit, but it's super noticeable on this one. Here's another titanium augite. Halo's not as pink looking because it's probably starting to go extinct depending on the orientation of this thin section when this scan was taken. And you can see there are a lot of minerals in here. We have olivine here, and of course our pyroxenes, and there's small plagioclase in the matrix. You can see all the plagioclase slaves here, but I don't really see any plagioclase phenocrysts anywhere, which is kind of unique because they're pretty common in the other ones. So here's an example of something I haven't talked about. We also have anhedral pyroxene crystal here. You can see a piece of it either didn't fully grow or is broken. But what can happen to minerals if they were originally anhedral and they get pulled into the magma conduit? Just like rocks in a riverbed, they can start rolling around in this magma mush and start eroding away. So essentially, an olivine that might have started off euhedral might get its edges and crystal faces removed, and it might become rounded as this thing's riding in the magma on its way to the surface. So that's what it looks like might have happened to this olivine. It looks like it's been rounded off on its ride up the magma conduit to the surface and eventually dumped into the lava. While a lot of other crystals seem to have survived, like this pyroxene here, you can see its crystal faces pretty well. And this is also another good example of something else I haven't talked about. You see these lines? It looks like there's a smaller crystal inside a larger crystal. Now, crystal collectors, when you get something like this, where it looks like there's a crystal inside a crystal, believe they call that phantoms. Now, in thin sections in metrology, this is called zoning. And basically, as this crystal was growing, there were small compositional changes that were occurring. And that essentially created the zoning that you can see, and geologists or mineralogists and petrologists can use this to understand what was happening or what the magma conditions were at the time that this mineral was growing and the different phases that occurred in that magma system. Something else you might notice, you see these little bubbles? Here's one right here. You can see all these little black dots. These are likely fluid inclusions or some kind of inclusion, so maybe a vapor phase, or maybe it represents the crystal or the melt phase of the magma. So if you have the right technology, petrologists or mineralogists, volcanologists can look into zoning as well as these inclusions to figure out what was happening in the magma chamber. This is why they will take samples of rock from volcanoes like Mount St. Helens, when Mount St. Helens was erupting, and even after the eruption. They studied the rocks that came up, and they were able to get a window into the magmatic system and get an idea of what was occurring before, during, and even sometimes after an eruption, and it gives us a good understanding of the volcano. And in this case, it can give you past understandings of ancient volcanism that is no longer happening. Again, I'm not an expert when it comes to these things, but hopefully I explained that well enough. It's really cool. So there's one more thing I want to show you, and as you can see, this rock, if you come over here, it's pretty altered. There's all kinds of, looks like calcite and idiomzite happening to the olivines. It's not very happy. But there's this weird grain I want to talk about here. It's completely dark because it's extinct. This is a quartz grain. And this quartz grain did not form the magma. It was incorporated into the magma. It was pulled into it. So this, since it's a large individual grain, would be known as a xenocrystal. If it was multiple grains fused together, essentially a rock fragment, it would be a xenolith. Since it's one large individual grain of quartz, it's a xenocrystal. Now, quartz is not going to be typically in a basalt. This did not form in the magma, but it got pulled into it, either as the magma was flowing on the surface or as the magma was racing up through the earth, through the country rock, whether that be a metamorphic or an igneous or sedimentary. It got pulled in the magma. Now, quartz is high in silica. Mafic magmas, like basanites, are low in silica, and that difference causes a chemical reaction to occur. And essentially, the crystal starts to dissolve away as it reacts with the magma. And if you look here, you can see there's a rainbow effect around this entire grain. And these are all pyroxenes that are starting to form in that reaction. So essentially, the magma starts to eat away at this quartz grain. In that reaction, you start forming this halo, this reaction rim, and you start to form pyroxene in its place. Again, this is not good when it comes to my geochemistry because you're adding a rock that didn't really initially start in the magma, but it's really cool to see that in thin section. So this is a xenocrystal that got incorporated in the magma, and the magma started to react with it, and you formed a pyroxene rim around that quartz grain. How cool is that? So I think I'll wrap it up here. I've been talking for quite a while, and I showed you all kinds of different things and explained all kinds of different scientific terms, and hopefully you didn't get lost in my science jargon blah. But anyways, I hope you found this informative, and I hope you enjoyed seeing all these minerals in thin section. It's not something you see every day, and I think it's really cool, and there's a lot you can learn about rocks by studying the minerals in thin section. Again, this is on a software, so I'm kind of limited, and you can do a whole lot more with an actual microscope, which would be really cool. But maybe that'll be a future project when I have more money and time, because I have hardly any time right now. Anyways, I hope you all enjoyed this video, and I hope to see you all in the next one whenever I get to uploading once again. So, until next time, you all take care.